Hi guys, let's finish up the erratic motion before we can attempt some questions on them. Right. So remember the last time we talked about going from position time graph to acceleration time graph, and we talked about going from acceleration time graph to position time graph. Right. I forgot to mention something, that you need to know something here. If you're getting, because we said the velocity time graph is the area under the acceleration time graph curve, right? Then that means here in that case that negative area actually I want to say the area under the area of 80 graph under, let me say, below the time axis, area of 80 graph below the time axis is negative. Right, so we're saying area of 80 graph below the time axis is negative. What do I mean by this? It means that I'm just going to do a rough sketch here, because this is just an addition to our previous video. Let's say this was our acceleration time graph. Let me just say here, now you have your acceleration going something of this nature. Right, so this part here, if you're going to get the area in between this time and then this time, for this part right here, this is going to be equals to negative velocity, right? So the velocity that you're going to get here from whatever time, let's say this is tx and then tz, and that area right there, if I'm going to say that, you remember this is your acceleration time graph, the area of a dt equals to negative v. Please note that. So that area under the curve, because it's below the t-axis, it's going to be a negative velocity. So when you're adding there your velocities, this you're going to minus, right? You're going to minus from the other areas. So you will minus it from this area here, which is on top, also this area here, because we are looking at the area between the curve and the time axis. So for the first part, it's a positive area, and also in that last part, it's a positive area. But then here we have a negative area. So if you have a negative area, it's a minus. Remember that. Even if this is a velocity time graph, if you have a negative area, it's a negative position. Right. Do I want to say that? Actually, can you get a negative velocity? I don't think you will get a, because the negative velocity it's just the direction that determines that it's negative, right? But with acceleration, when it's decelerating, you get a negative acceleration here. Then you have to minus from your velocity, right? Because your velocity is getting reduced in that case. That's why we are minusing from it. It's deceleration. So this relationship, I would say it applies for the acceleration time graph going to the velocity time graph, right? Because your velocity, I don't think it can be negative unless we just change the direction. It's gonna be a negative, but then that means that now in terms of your position, or actually you can still minus your position, because we are looking at the displacement, unless we are looking at the whole distance. Let's say this was there, sorry, let me make a certain example here. This is your velocity time graph. Let's say it starts there, and then suddenly I change direction, and then now I'm here. Right, so I have a certain velocity here, I had a certain velocity there. This was going to be my initial displacement, right? Because it's the area under the curve. But then now in this case here, this is gonna be my change in position there, and then the change in position now is gonna be this one, but it's negative. I'm gonna minus it from that one. So if that one is a1, therefore this is gonna be my a2, and then to get therefore the change in position, sorry, the position as a whole is just gonna be equals to the first area minus the second area, a2, right? So it's the same thing with this one. If this one was a1, this is a2, this one is a3, then you would have your velocity equals to a1 minus a2 plus a3. So you add the areas which are above the x-axis and then you minus the areas below the x-axis. So please remember this when you do these derivations, right? It's something I didn't mention on our previous video. Okay, now that we have gone past that, let's talk about given the acceleration position graph. Now let's say this is what you're given. So if you're given the acceleration position graph, the only thing that you've got to remember is that ADS equals to VdV, right? So from here we can get our stuff. So let's see here, this might be the graph of yours, right? And then I'm gonna assume something here, doesn't really matter. That is your acceleration time graph, sorry, acceleration position graph, second squared, right? So right, in this case what you're gonna do is you do the same thing. It's your areas that we're interested in here. So we might do certain partitions from here. So right, and from there, and from there, and from there, and your velocity is still the area under the curve here, right? But then now we can use which equation to get that velocity? So we can say that this is gonna be t1 and this is gonna be t0 and then this is gonna be t2 and so on. For my velocity there, I will get something of this nature. I will have let's see, they said that ADS equals to VdV. To get V here on its own, I will have to take an integral on both sides because this is the differentiation with respect to velocity. So I'll have to just take the integral on both sides. And then noting that my S0, let's assume that the initial position is given to us. Okay, I see now what my problem is. I am still using a velocity time, a acceleration time graph. That is your position there. It's not your, this is S0, S1, S2, S3, S4, and so on. So here your S0, let's assume it's given, and let's assume you do know also your initial velocity. And then now this was going to be your final position, which is going to be S1 because we want the area between S0 and S1. And then here we're going to have V1, right? So that's just the case there. So to get your velocity, remember if I take the integral of this, the integral of V is just going to be half V squared. So I'll have half delta V squared, right? Which is just going to be half V1 minus V2. Sorry, it's V2 minus V1. Actually, it's V0 minus V1 because I'm using V0 and V1 here for the first area here. V0 minus V1, and then that is your integral there. Is going to be equals to for this side. Then here, taking the integral of this thing is going to be just integral of a, because a is a function of s, so I do not know what it is. I cannot take it outside. I'm just going to leave it as ADS from S0 to S1. Then this is how you would get your velocity. So you just need to solve for this thing here to get your V1. Let me just put it actually. So therefore here I can say, therefore V1 is going to be equals to that thing right there, which is your integral from S0 to S1 of ADS and multiplied by 2, right, to get rid of the half there. So I'm going to say 2 of that. So multiplied by 2, and then I'm going to add V1, right, V0 plus, because I'm interested in V1, so this is going to be V0. Okay, I want you to note something here. Keep on making these mistakes here. This is V1 minus V0 because it's final minus initial always. Remember that. So that's why I'm able to end up with something of this nature. Right, and then let me just put it in a box to show this is your final equation. So to get your successive velocities, you can just do that thing there. Right. This is how now you can get your velocity given the acceleration position time graph. You know ADS is equals to VTV. So from there, take the integral on both sides. You will end up here. That is going to be your V1, right? And then now if we were to draw this thing here, you know how it's gonna look. It's gonna be just something. So your velocity position graph. All right, it's the same thing. So I'm just gonna do a random curve here. All right, and then in this case now, the only thing that I want you to note is that V1 point. So you can have your V0 here, and then your V1 probably there, depends on the partitions. Then here is gonna be your V2. But as long as you know you use that equation to get your V1, and to get V2, that is going to be V1 there. So it's V2 is equals to 2 times that integral plus V1. For V3, it's plus V2. For V4, it's plus V3. So just that there. And then you'll be able to get your velocities. Right, so that's your velocity there, meters per second. And this is your position in meters. Right. So this is how you would get your velocities. You just use that equation and then you'll end up here. But now it's the same thing for your position. We have already talked about this one because you have that now as a function of s. Right, so okay, you get your velocity now as a function of position. That is fine there. Okay, these are the only two graphs that we have to look at when it comes to acceleration position time graph and velocity position time graph, because we cannot look at position time graph, right? Position graph, right? So we're looking at velocity position graph, acceleration position graph. Now that we have looked at that, right, those are the derivatives. But then now let us assume you want to go to acceleration, right? You're given this velocity position graph. One thing you can note here is that also the equation is the same, right? You got your ADS equals to VdV. How do I get acceleration there? So your acceleration equals to VdVds. Right. So that is just going to be your acceleration. But now what is dVds? Remember, if I were to take the slope of this graph exactly at that point, I will end up with something of this nature. Sorry. So that is going to be my slope, but then this right here is your dV ds. The rate of change of my velocity position graph is that dV ds. And what is my v? If I'm using that point for the derivative, I just look at the height of v. What is v there? You come and you trace it back here to your velocity. Then here, that is your v that you are using in your equation, right? This is the v that you're going to use here. And then the dV ds is just the derivative of that function. So you see, if you're given the velocity position graph, you can just take the derivative of that and then multiply it with that velocity at that point, right? Which is it has to give you a certain value at that point. So you would plug, let's say maybe they said s is equals to 2, then you would plug in your velocity position graph 2 to get the velocity, and then you take your derivative of that position time graph to get your acceleration, right? So this is just how you can do it, as long as you know that position time graph, acceleration time graph, or position, velocity position graph, and then also acceleration position graph. You can use these equations to go to your velocity and that equation to go to your acceleration, right? So that is just going to be the KCM. So if this is going to be your V1, this is the same thing. If your A1, this is V1. That's just that. It's the same velocity that we're using. Right, now that we have described that, what else is left? I think that's all. Right, so that's it with our erratic motion. We have described all these relationships. I think we can end it here and then we'll do questions on the following ones. Right, thank you.